Hello and welcome to this fourth video in our lecture on the TLS protocol. Before we go ahead and dive into that actual real-life protocol, I wanted to present one more simplified or made-up protocol to give you more practice with studying the strengths and weaknesses of such protocols, which is a very good skill to develop, especially before we study an actual protocol. So this protocol claims to be doing it all. Notice it's supposed to enforce mutual authentication, to allow us to establish a session key securely, and it also supports perfect forward secrecy. So this algorithm is a modification of our earlier encrypt then sign protocol. So notice that this protocol uses the RSA algorithm, say, in order to sign and encrypt these messages. And then it will also use the Diffie-Hellman algorithm to establish a session key to be used in the rest of the session after these three messages are completed. So it's a very similar algorithm to what we discussed in the previous video, but I want you to study it carefully and make sure that you understand the best possible answer to these questions. So the way that this algorithm works is Alice initiates the protocol by sending her identifier and then a nonce, a random number that she selected. Bob is going to receive that identifier and that nonce. It's going to also compute using alpha q and its own x sub b number, his own y value, y sub b. And so it's going to concatenate this y value for the Diffie-Hellman algorithm to the nonce or the challenge that Alice sent him. He's going to take this concatenated string and encrypt it using Alice's public key. And then he's going to encrypt it again using his own private key. So make sure that we are in an encrypt then sign framework here. And on top of this message is also going to generate a nonce and send that random number to Alice as his challenge to her. Alice is going to receive this challenge. She's going to use it to generate her own response. She will also access and get the value y sub b from Bob, which will allow her to compute the shared key that is the end result of the Diffie-Hellman algorithm. Now, of course, before that, she picked her own x sub a number. She computed her own y sub a number, and she's going to send it to Bob. So that's what she does in the third and last message of this protocol. She's going to take the challenge from Bob. She's going to concatenate that to her own y number, and then she's going to encrypt the resulting string using Bob's public key and then using her own private key. These are the RSA keys, as we discussed before. These are the Diffie-Hellman elements. So when Bob received the third message, he will be able to decrypt it using Alice's public key, then to decrypt it again using his own private key. He will therefore have access to y sub a and is going to use it in conjunction with his own number x sub b and alpha and q to compute the same shared key, which will be therefore established at the end of these three messages. And remember, this is a symmetric key that both Alice and Bob are going to use in the rest of the session to encrypt all of their upcoming messages. So this is a symmetric key or session key. So in a nutshell, this is how this proposed protocol works. Now I want you to pause the video and think very carefully about the best answer you can come up with for these 5 questions. Okay, so the first question is, why is it true that Alice is authenticated to Bob in this protocol? Well, the authentication of Alice to Bob is performed essentially with this operation, because this is the operation that, according to which Alice is using a private key, which only she knows, to essentially sign this third message. So when Bob decrypts it using Alice's public key, we'll be able to check that she did send him back his challenge as part of her response, and therefore it will have authenticated Alice. Okay, so how about the second question? How is Bob authenticated to Alice? Well, this is kind of a symmetric question, but in the second message, Bob signed it using his private key. Since he's the only one supposed to know this private key, then when Alice decrypts it using his public key, she will be able to eventually access um, her challenge, which she has sent to him earlier, and she will be able to guarantee that Bob is the one who sent her his response. All right, so the first two questions seem reasonably simple to answer. However, I still want you to be checking that there's no way to break this scheme, this protocol. But let me continue for now. So how do we know that the session key is secure? Remember, the session key is this case of AB, and we want to make sure that nobody else is allowed to access it besides Alice and Bob. Well, here you could answer maybe two different things. First of all, notice that the message that Bob sends to Alice is encrypted with Alice's public key. Therefore, only Alice is going to be able to decrypt it and access the Y value. Similarly, when Alice responds to Bob in the last message, she uses his public key, so only Bob is going to be able to decrypt this message. But actually, so in particular, that means that nobody but Alice and Bob are going to be able to know the YB and YA. But actually, I should remind you that maybe those encryptions are not necessary, at least for this part, because remember from our previous discussion of this hybrid type of algorithms, Diffie-Hellman is supposed to be secure because of the discrete logarithm problem. Therefore, even knowing the values of these two Y values, there would be no way for the attacker to determine the session key. So really, the true answer is probably considered to be the values of Y themselves, and this encryption step is maybe a redundant step when it comes to this question. Nevertheless, I want you to think if there's a way to break this kind of double protection. Okay, fourth question. Why does this protocol support perfect forward secrecy? Well, the reason is the same as before. This is a Diffie-Hellman, authenticated Diffie-Hellman algorithm. As long as we use an ephemeral version of it, that is the so-called DHE version of it, then perfect forward secrecy is going to be enforced, because remember, at the end of this session, not at the end of these messages, but after all the messages are being encrypted with the shared key, the two parties are supposed to delete both the shared key and their private values, x sub a and x sub b. This is the whole point of an ephemeral version, where the symmetric keys that are used for the encryption in the rest of the sessions are deleted as soon as the session is over. This means that any attacker that recorded those messages and is willing to wait long enough into the future until they're able to break into, say, Bob's system, they won't be able to access the key or the X value, so they won't be able to decrypt any of those session messages that follow. Notice that the beauty of this perfect forward secrecy is that after the session is over and these keys are destroyed, Not even Alice and Bob are able to decrypt their own earlier messages. So if Alice and Bob cannot do it, clearly an attacker cannot do it either. So just make sure you review the concept of perfect forward secrecy from the previous video if needed. Now, finally, have we prevented replay attacks? So I'm going to claim that this is the case. And the reason for that is the use of nonces. Remember, a nonce is a number used only once. So even if the attacker would record those messages and replay them later, there would be a problem because, for example, if the attacker would replay this message pretending to be Bob, there is no way that Alice would have sent the same nonce in that new or future version of the protocol. And so whoever was impersonating Bob would have sent the wrong response nonce, not corresponding to the challenge nonce. And of course, the same is true for this pair of nonces, or this nonce used in the pair of messages coming from Bob and back to Bob. So this is how this protocol claims to avoid replay attacks. So again, this is not a real protocol. This is a made-up protocol that I want you to try to break. So please let me know if you have found an attack, a successful attack on this protocol. Let me know if you're able to counter any of these claims. If not, make sure you develop your analysis and cryptanalysis skills, because in the next video and really the rest of the lecture, you will be able to apply those skills when we discuss a real world, actual authentication algorithm that claims to have all of these properties. And this protocol, not this algorithm, but this protocol is called TLS.